Alright, so now we're into section 9.3 and we're going to talk about confidence intervals. So this is just like chapter 8 except for the formulas are going to be a little bit different. So remember, what a confidence interval does is it's going to be a technique that's going to say, hey, we found this using the sample. Here's what we think it says about the population. And with that, we get two pieces of information. One piece is that we're going to get an interval on which we think the population probably lies. And then we're going to tell people how confident we think, how confident we are that the population is actually on that interval. So for example, if we have a 90% confidence interval, then we're 90% sure that the population is somewhere on that interval. It means there's a 10% chance that it's not. So confidence intervals are very useful anytime we ask the question, what's the typical value for a variable in this large group of objects or people? And how far away from the truth might this estimate be? So, suppose that we're using a survey, which is a sample, and we find that the mean commuting time in Bremerton is somewhere between 10.5 minutes to 23.7 minutes, and we say that with 95% confidence. See? So, that means that if we were to take the mean commute time for every single commuter in Bremerton, we would be saying with 95% confidence that average for every commuter would be somewhere between 10.5 to 23.7. So we say that we say that mu is probably somewhere in there. So if mu equaled, say, 20 minutes, then that's great because 20 minutes is on this interval. However, if we actually found the mean commuting time for every person in Bremerton, and we found that their average was 25 minutes, well, that would be where that 5% chance of an error can occur because 25 is not on that interval. So, how do we calculate the confidence interval? Well, you are going to take your sample average, and you're going to plus or minus t times s divided by the square root of n. Now, just a reminder, this is your standard error. Okay, so x bar is your sample mean, s is your sample standard deviation, n is the size of your sample, and now your question is probably like, hey, what's t? Well, what t is it is a test statistic. What you can relate this to is it's very similar to a z-score. So here's the thing, is that the t is going to be a multiplier that's going to come into play, and it's going to determine the level of confidence we want. So remember, when we're looking at confidence intervals in Chapter 8, if we wanted a 95% confidence interval, we'd have a z-score equal to 2. If we wanted one of 68%, we'd have a z-score equal to 1. So the difference between Chapter 8 and Chapter 9 is in Chapter 9, the t-value actually depends on the size of our sample. So it's not just 2 or 1, it has to do with the level of confidence and the size of our sample. And that's because our distribution is going to change shape with something called degrees of freedom. So you guys don't really need to know this, but what degrees of freedom are they are the amount of ways objects or people in our sample can differ. So the reason it's n minus 1 is because there's one thing that everybody in our sample is going to have in common, and it's kind of silly. The thing that they have in common is that they're all part of the sample, so they automatically lose a degree of independence. So how do we find the t-value? We use a table. Note, however, that this is super tedious, and now we use technology. You guys are super lucky I didn't get to use technology, I had to use a book. So, for example, a study to test the life of iPad batteries reports that in a random sample of 30 iPads, the mean battery life was 9.7 hours, with a standard deviation of 1.2 hours. The raw data was not made available to the public, so we don't know what the actual population was, we just know the random sample. So what we want to do is that we want to use this table to find the t-value for a 90% confidence interval. So here's what we know, is we know that x bar, the average from our sample, is 9.7. We also know that the standard deviation was 1.2. Okay, we know that n was 30, And we also know that the degrees of freedom is n minus 1, which in our case is going to be 29. So to find the 90% confidence interval, okay, we're going to have x bar plus or minus t times our standard deviation divided by the square root of n. So we're going to have 9.7 plus or minus, and then s is going to be 1.2 divided by the square root of 30. But don't forget, we need to multiply that by t. So we want to do 90 degrees of freedom, or I'm sorry, 90 degrees, 90% for a confidence interval, and we're going to have 29 degrees of freedom. So that means that our t value is going to be this guy, which is going to be 1.699. Alright, so when we do the math for this and we work it out, here's what we're going to get. We're going to get between 9.33 and 10.07. So what this means is that we are 90% sure. So this means that we are 90% sure that the average battery life is somewhere between 9.33 and 10.07 hours. Alright, so for the next one, the average cost of gasoline in 2009 was 2.07. Today, a random sample of 40 gas stations found that the average gas price was 2.78 with a standard deviation of 0.43. Now what we're going to do is, instead of doing this by hand, we're actually going to be using StatCrunch. Okay, so here's how you're going to use StatCrunch. You're going to go Stat, and we're actually going to go to T-Stats, one sample with summary. Now, if we look back at this example, we're going to have a sample mean of 2.78. We're going to have a standard deviation of 0.43. And we looked at, how many gas stations did we look at? We looked at 40 gas stations. Now, when you do this, be sure that you hit the confidence interval. Okay, that's when you want to select. And we want our confidence interval to be 90%. And then we click that, it's going to come up with this. So on the notes, you can see that we have the same thing. And the lower limit and the upper limit, that's going to be our bounds for confidence interval. So first off, is 2.78 a parameter or statistic? Well, since it came from a random sample, it is going to be a statistic. Okay. The next thing we want to do is that we want to verify that the conditions are valid for the confidence interval. So, first of all, was it random? Yes, because we said so. Second, our sample size is greater than 25. So we nailed it. Alright, and last but not least, we want to make sure that we have enough gas stations. So, do you guys think that there's more than 400 gas stations? Yes, there's more than 400 gas stations. So, we are good. The next thing is that we want to know, does the confidence interval show evidence that the gas price, or that the price of gasoline has changed since 2009? So if it was the same, then we would be 90% sure that the cost of gas was somewhere between $2.60, well, we'll say 67 cents, and $2.89. Now, since $2.07 is not even close to being on this interval, then what that says is that we do have evidence that the gas price has changed. Alright, very last one. We take a random sample of 29 pizzas at a pizza place, and we find that the average diameter is 12 inches with a standard deviation of 0.3 inches. We want to find a 95% confidence interval and interpret the values. So, again, we're going to go back to StatCrunch because doing this by hand is so tedious. Okay, we're going to go to T-Statistics, one sample with summary. Alright, so on average we had 12 inches with a standard deviation of 3 inches. And how many pizzas did we look at? We looked at 29 pizzas. And we want to find a 95% confidence interval. So when we do this, we're going to get a lower limit of 11.89 and an upper limit of 12.11. So what that means when we interpret the values is that we are 95% confident that if we took all the pizzas ever produced from this restaurant and took their average, that the average would be somewhere between 11.89 inches and 12.11 inches.